let's get started. First of all, let's recap what we learned last week. We discussed the QPSK as an extension of BPSK, right? You see here the picture here, the binary PSK, also the picture constellation plot of QPSK. 펜이 없네. 미안한데 옆에 어디 발이 가서 좀 이거 펜 좀 조금 어디 좀 빌려줘. 펜이 하나도 없네. Okay, so let's take a look at the constellation plot of BPSK. So we have binary 0 and 1, which will be mapped to symbols. So here are two symbols, S0, S1. And S0 is negative, S1 is a positive amplitude. So this is the form of antipodal signal, right? So you have same amplitude. You see that it is a radius, right? So this distance and this distance is the same. So distance is same. The only difference between these two symbols is that this is a positive symbol, this is a negative symbol. So that's antipodal signaling, right? So BPSK is antipodal, same as antipodal signaling. However, in QPSK, what you can see is that you will see 4 different symbols because that's a quadrature. And this is a PSK because each symbol has a different phase. So this is like a 45 degree, 135 degree, something like this, right? Each one has a different phase. However, what you really want to make eventually is that the modulator will create the cosine term and also the sine term. So for example, this particular symbol has this amplitude cosine and this amplitude sine, right? When you combine the cosine of this term and also the sine of this term, that is going to be this symbol, right? That's how you create. This particular one, for example, right? If you want to create this symbol, what you can do is that you will have this amplitude minus cosine and this amplitude sine, right? So this is like a minus, so this symbol is going to be this times cosine and that times sine. And you add them together, right? Minus cosine plus sine, that's going to be this symbol. That's how you create the QPSK, simply speaking. Now, this mapping, this shows you how to map between bits to symbol, right? Since we have 2 bits in this case, eventually 2 bits will be mapped to 1 symbol. Then the question is, which 2 bits is going to map to which symbol? So this is going to be showing how to map it, right? 0, 0, 0, 1, 1, 1, 1, 0. And one thing that you want to remember when you map bits to symbol is the gray coding, right? So neighboring symbol, for example, this one and this one is a neighboring because distance is smallest, right? The smallest distance. This one is not neighboring because this is a little bit large distance, right? We are only looking at the 2 symbols, neighboring 2 symbols with the smallest distance. That's what we always worry about. So this one has a small distance and this one is the same distance. So these 2 are neighbors of this guy. So when you look at the neighboring symbols, you see that there's only 1 bit difference. 0, 0, 0, 1, 1 bit difference, right? Look at this one also. 0, 0, 1, 0, only 1 bit distance. That's what you want to do. And that's the gray coding. So remember the gray coding. And this is the case of QPSK, but we also learned the 16 QAM, right? We have 16 symbols. Even in 16 symbols, you still have a gray coding. Okay, always the neighboring symbols will have only 1 bit difference. Okay, so that's a gray coding. So this picture shows you how to do gray coding in case of QPSK, and also how you place the symbol in the constellation plot. What is the phase for each symbol, right? And what is the energy for each symbol? So you can see all of this information in this picture. Okay. So this is a 16 QAM, as I said. So QAM, quadrature amplitude modulation, is different from QPSK or any PSKs. This is not PSK. So PSK is the modulation when where you have where you have the information in the phase. So PSK is a phase shifting, meaning that your information is in the phase. This is amplitude modulation, but this is quadrature amplitude. So which means that your information is also in the amplitude. So when you look at this constellation plot, what you can see is that when you look at these four symbols, these four have a different phase. Each one has a different phase. So phase has information, but when you compare this symbol with this symbol or this symbol, you see that the amplitude is different. This one has this amplitude, this one has a very large amplitude. So amplitude also has information. So this particular, we call this a QAM, QAM, QAM. This QAM modulation has a phase and amplitude. Both has information. So when you look at every 16 symbol here, each one has a different amplitude with a different phase combination. Okay? So that's how you differentiate each symbol. And also when you look at the mapping, bit to symbol mapping, look at here, for example, this particular one. Who is neighbors? Who are the neighbors? For this particular symbol, this neighbor, this is neighbor, this is neighbor, this is neighbor, right? We have 4 neighbors. And compare the bit mapping. All the neighbors will have only 1 bit difference because this is based on the gray coding. Okay? So all those information is in here. But one thing that you want to remember is this QAM modulation, you also have to measure the amplitude. Amplitude is also important. Phase is also important, right? When you look at this one and this one, these two has the same phase. So you need to detect the phase because the phase has information. You know, this one has the same amplitude but different phase. So we need to detect the phase. Not only that, we also have to measure the amplitude. You have to detect the amplitude because this one has the same phase. Then how do you find out, how do you differentiate these two, right? You need to detect the amplitude, both of them, amplitude, phase. So that's a QAM. This is very popular. Your phone, the LTE phone already is using this. Your LTE phone is using QPSK and this 16 QAM already in your phone. So very popular modulation. Let me skip these things. Okay, so let's review briefly about BPSK block diagram. You see this one in the midterm exam, right? You've done a midterm exam. The only difference between this picture and the picture in your midterm is that you have a phase here. Everything else is same, right? Everything else is same. Only difference is that you have a phase term in the midterm, okay? Which means that you need to consider the phase, right? So I'll see what happened in the midterm. But even though you have a phase here, everything else is same. What that means is if you have no phase like this, right? You multiply the cosine, and then you get this one, right? Some amplitude with the cosine, with the phase 0. That comes in here, and you are multiplying same cosine with no phase again. So right here, okay, right here, in this picture, right here, you will see cosine square, 2 pi fct. So with some amplitude, right? That's what you're going to see. However, in the midterm, what you're going to see is that you have a theta term here. So what you're going to have here is same thing. Cosine 2 pi fct, which is this one is already multiplied here. That is received, and you're going to multiply this one here, cosine 2 pi fct plus theta. That's what you're going to do. Right? Same thing, same. Once you have this, right, eventually you're going to do integration. But when you do integration, this is going to be cosine times cosine. So based on the identity, you can change this one into cosine alpha plus beta minus cosine alpha minus beta, something like this, right? You can change this into that. Then this first term is alpha plus beta. So you add these two, you have a 4 pi fct plus theta, and this term is minus. So the second term is going to be only theta. but you do integration, so this will go away because we have low pass filter. This will be gone anyway. This one is the high frequency component. So what is remaining is this cosine theta. That will all populate to the end. Right? That's why in the question that I asked you one of the sub question that what is the range of the data rate, right? That's because that we have a theta. Theta can be any value from 0 to 2 pi, any value. So unfortunately, if theta becomes 90 degree, you're going to get 0. Because this one is 0, 0 is going all the way, eventually it's going to be 0. So 0 is the worst case. And the best case is that this cosine becomes 1. That's going to be best case. So that's the range. So all the processing, all the calculation is exactly the same. So if you do it this way, then you're going to get the score. Okay. So anyway, that's what's happening. So this is a BPSK. Now we're going to look at the QPSK. Okay, QPSK. Well, QPSK is also same. The only difference is that we're going to get the 2 bits coming in. So these 2 bits, for example, 0, 1, 2 bits coming in, this particular block, which is doing mapping between bits to symbol, this block have information about this constellation plot here. So 0, 1 is going to map to this symbol, and this symbol has minus cosine and plus sine. So what's going to happen is that based on that mapping, we're going to create minus cosine, minus cosine, and plus sine. So we're going to have that value here, right? Based on the mapping between bits to symbol. So we have cosine component, and also we have a sine component here. Now this cosine component goes up, and sine component goes down. So the cosine component, which is this one, goes up, and sine component here goes down. And then we're going to multiply the cosine, and we're going to multiply sine here. Then eventually, right here, after the multiplication, we get this cosine 2 pi fct. We get sine 2 pi fct. Now we know that cosine and sine is completely orthogonal. So what that means is you can just add and transmit. Still at the receiver, we can completely separate them because those are cosine and sine is completely orthogonal. You can add them together, no problem. Perfectly, we can differentiate perfectly at the receiver. So that's the structure of QPSK modulator or transmitter. But when you look at it carefully, what you can see is that this particular one, we have I channel. This I channel is this I channel. This I channel is completely same as BPSK. This Q channel is also BPSK, but this BPSK is using sine as a carrier. This is a cosine carrier, so perfectly same as QPSK, the BPSK. This is also BPSK, because when you use a sine as a carrier, when you look at that in the constellation plot, that means we are using these 2 points as your symbol. But as I said earlier, you can rotate, no problem, right? Performance is same. You can rotate, doesn't matter. So this one is actually same as a BPSK. Same as BPSK. BPSK. So it's basically same as we're going to put the two different BPSK in parallel. Okay, so that's what it is. Now this is a modulator or transmitter. Once you create this kind of signal, now let's say we create cosine 2 pi fct plus EB over square 2 sine. This is what we transmit. We call that as ST. So we transmitted this signal based on this modulator. Now we're going to receive that in here, the receiver. Okay, this receiver. This particular receiver. So this ST is going to be received here, and now that ST is going to be split it into here and here, I channel, Q channel. This is a receiver, right? We still have I channel, Q channel. In the I channel, we multiply cosine. In the Q channel, we multiply sine. So when you multiply cosine here, this is going to be cosine square. This is going to be sine cosine. This sine times cosine will be 0 anyway when you integrate, because sine times cosine, sine theta, cosine theta, eventually it's going to be like sine 0 plus sine 2 theta, something like this, right? Eventually. So sine 0 will be 0 anyway. Sine 2 theta, when you integrate, it's going to be gone anyway because we have a low pass filter here. So anyway, this term, cosine times sine, will be gone anyway. That's very straightforward. Why is it gone? Because orthogonal. These two are orthogonal, right? So orthogonal meaning that when you multiply these two, it's going to be 0 anyway. So because of this orthogonality, this is going to be 0. And we have cosine square. Cosine square term will only go into low pass filter. Eventually, only the high frequency component will be gone by low pass filter. So what is remaining here is the same as BPSK. Same thing here. Still, this ST comes in here, we multiply sine. So we have sine square, cosine sine. Cosine times sine will be gone. And sine square, same way, only the DC component will pass, low pass filter. So we combine them together, and then we make a decision for each of them, because each one is same as a BPSK. And BPSK, what is important is it going to be plus or minus? Plus or minus? That's the BPSK, right? So let's go back to the BPSK. Eventually, what you need to do at the receiver is that when you look at the BPSK, right, one is positive, the other one is negative. So when you make a decision at the receiver, what you need to make is that just to detect the sign of the received energy. Is the received energy positive or negative? That's a simple decision. That's what you need to do, right? Same thing for the QPSK. Because QPSK, we split it into two different BPSK. Each one is the same decision as BPSK. Plus, minus. This one also, plus, minus. Maybe this is plus. And if this is also plus, right, then what does it mean? If the decision from both of them are plus, that basically means that you receive this point, right? If the I channel gives you minus energy, and Q channel gives you plus, that means I channel is cosine. That is minus, so somewhere here, right? And Q channel gives you plus energy. That means energy, the up here. So that in that case, it's going to be this one. I minus from I channel, plus from Q channel. That's going to be this symbol. And so once you receive that, once you receive the minus from I channel, plus from Q channel, that means this is received. So once you receive this one, what is going to be the bits eventually? 0, 1. So you're going to recover 0, 1 as the final bit. So that final decision will be going here. So eventually you're going to decide plus minus or minus, and then eventually change it to bits. That's going to be your final answer. Okay? Yeah. So that's what's going to happen. There was a question last week. The question is about what if we have a phase difference at the receiver, right? Actually, that was the question that we have in the midterm, right? Let's go back to the midterm. In the midterm, as you know, we have theta here. That basically means that transmitter just multiply cosine with the phase 0. But receiver, receives some unknown phase, some arbitrary phase. Does it make sense or not? This always happens. This is always happening. In this picture, right, we just want to make it simplified. We just want to understand the idea. That's why we just ignore the theta and then make it same, right? Make it as a same as a 0. Both one are 0. So what that means is we intentionally make this one as a coherent. This one means coherent, right? We have a phase exactly match. Phase 0, this one also phase 0. Transmitter, receiver, both of them have phase 0. That means coherent. So we make it coherent on purpose. But in actual scenario, that's not going to be true. In real system, we're going to have some unknown phase, like this, right? We have some unknown phase. This theta can be any value. This theta, the range of this phase difference is going to be 0 to 2 pi, right? This theta can rotate any value. Because of the channel, because of the noise, because of many of things, this theta is completely random. Completely random. Now the question is, if this data is random, then how do you detect the signal? That's the question, right? Then that's also the question in the midterm. So eventually, when you have a theta difference, eventually your output will be a function of theta, like a cosine theta. Cosine theta should be in your answer, right? Of course. But as you can see here, when you have a cosine theta at the output, and theta is random, then because of this random value, sometimes you get 0. Sometimes you get very high value. Sometimes this one becomes 1 over 2. So it should reduce. Which means that your amplitude changes. Sometimes 0, sometimes 1, sometimes half. Something like this, right? And this data is random. We cannot control it. So certainly that's a problem. And that happens, really. Now the question is then, so that means this is not coherent, right? Because phase is different. This one is a phase 0, but this one has a phase theta, which is random. This is not coherent. Now then, how do you make these systems to be coherent? That's the question, right? In other words, we cannot make theta as random, because if theta is random, our output is changing, so we cannot do it this way. So what that means is we have to detect, we have to find out this data, and we have to correct it and make it coherent. Okay, once you detect this data, we can subtract it out, and we can make it coherent, right? Once you find out. Now the question is, how can you find out this data? That's the question. Some of you heard about the Costas receiver, right? Costas receiver. When you learned the analog communication last semester, your book probably shows you the Costas receiver. So you probably learn about Costas receiver. So simply speaking, Costas receiver is the receiver to detect the theta. If you don't have this structure, there's no way. In this structure, right, we basically we are seeing a very simple BPSK receiver. This BPSK receiver has no way to detect the theta. You cannot detect the theta. So this is very simple design. Okay, this is not going to work because the output changes. So what you need to make is that you have to have a certain Costas receiver structure. There is a certain structure inside this receiver. You should have this. If you don't have this, it's not going to work. Okay? This works only based on the assumption that theta is 0. Okay? It works only under that assumption. But that assumption doesn't make sense because this theta is random in reality. So that's why it is important to understand this receiver. This receiver is a little bit complex, but it's a practical receiver. It's very important to understand this one. But before that, let's take a look at it. I don't have that structure here, right here. So let's go ahead and understand the QPSK first and how to simulate, and then tomorrow let me introduce this costless receiver. But the idea here is that you need to detect the theta. In that way, we can say it's coherent. So we're going to come up to the costless receiver tomorrow. Okay. So let me just go ahead. So this picture again, this is a QPSK receiver, right? This QPSK receiver works as ideal only when you have no phase. See, this one also has a phase 0, right? Transmitter, we assume transmitter. This is transmitter. Transmitter, you can make any phase. Make it 0, no problem, because the phase is going to be rotate anyway in the channel. So it doesn't matter what phase you have. In that case, why not make it 0? 0 is simple, right? So transmitter always make a phase 0, no problem. The problem is the receiver, right? After transmit, the signal goes into the channel. This channel make some random phase, right? And that's what you're going to receive here. So always the receiver, we have random phase added onto it. So that's the problem, always. So that's a problem with receiver. So we need to have this costless receiver. We're going to look at that tomorrow. Okay? So for now, for today, let's assume that we have coherent. Okay? And then let's move on. This slide is going to show you, it's going to visualize what happened when you do the BPSK. But this picture is going to show you how to do simulation. What we learned so far is just block diagram and just the equation. That's the only thing we learned, right? That's what you see in the book, our textbook. But all of these things can be simulated in computer. You can actually do it by simulation. You can make a MATLAB code to do simulation. This is the result. So let me just introduce you how to do it. We have a transmitter. In this case, this transmitter is a BPSK transmitter, but you can also do for QPSK. Okay? But this is simply for BPSK, just to give you an idea. BPSK transmitter, let me write it here, BPSK transmitter in this case. This is also BPSK receiver, just as an example. So in the simulation, we create transmitter in the MATLAB simulation. And this transmitter, what you do is that you create a bits, because everything starts from bits. We create a bit sequence in your MATLAB. And based on the constellation plot, like this, you see that this is a symbol 0, symbol 1. This is a constellation plot, but I just plotted into MATLAB. Okay? This is the picture like, this is a constellation. I just plotted into MATLAB. Okay? So based on this constellation plot, you're going to do a mapping between bits to symbol, okay, in your MATLAB. And then you transmit. But transmit doesn't mean anything in the MATLAB simulation. MATLAB simulation, you just create a vector. That's it. So this transmitter actually is just a couple of lines, maybe 2-3 lines. That's it. That's all you have in transmitter. Very simple. Now when you have this transmitter in the simulation, we transmit that into the channel. But transmitting is nothing in the simulator. Simulator, we are not actually doing simulation, right? You just create the vector, transmit signal vector x, that's it. What's going to happen in the channel is that we can add some noise. So we create some noise samples, right? Noise samples. But our noise is AWGN noise. And in MATLAB, there is a function called the rand_n. Random variable. The n means normal. So rand_n is the function to create some random samples based on normal distribution. So when you call the rand_n function in MATLAB, you will create some random samples based on the Gaussian distribution. So that's what you need. So once you use this rand_n function, we can create noise samples, right? Of course, your noise samples, number of samples should be the same as the number of samples in the X, right? This vector has a size, right? Maybe you have 1,000 samples, right? That depends on how many bits you create. So if you create 1,000 bits, in BPSK, 1 bit to 1 symbol, so you have 1,000 bits originally, then doing this QPSK, the BPSK, you have 1,000 symbols, X. X is a vector with all symbols, but size is 1,000. Now you create 1,000 noise samples, same size, and you just add it. That's what you're going to receive as Y. And this Y goes into the receiver. Inside the receiver, now you have to do decision. And in BPSK, what's the rule for decision? Decision is going to be like, is it positive, negative? That's only decision. If the positive, then you make a decision as S1. Negative, S0. That's simple as that. That's what you have here. Now, what you see in this picture is the MATLAB simulation. See that when you create at the transmitter, there's no noise, right? For example, you have 0, 1, 1, 0, 0, like that, right? That's your bit sequence. Maybe you have 1,000 bits. Now, what's happening inside the transmitter is that you look at one by one, and then based on this mapping, you just change it. For example, if this one has amplitude 1, this one is amplitude 1, that means it's -1, -1. That basically means that if you map it into 0 to this and 1 to this, so this one you can decide. Maybe you can do a mapping 1 to S0, 0 to S1, if you like. Or you can do like 0, S0, 1, S1. You can do it you can do whatever you want, right? You can do cross mapping, that's okay. So if you want to do this mapping, now what's going to happen inside the transmitter is that the first bit is 0. 0 is mapped to S0. S0 is -1. So the first output is going to be -1. Second bit is 1. 1 goes into here. Based on this mapping, our output is going to be +1. Something like this, right? This is what this X vector looks like. That's what you transmit. Now you already create the noise samples, right? Based on normal distribution, Gaussian distribution. That is going to be like 0.3 minus 0.1, something like this. This is what your noise vector looks like. Now you're going to add it, and then you receive Y. So this Y, it looks like you're adding these two. So once you add these two, right, -1 plus 0.3, it's going to be minus 0.7. So it's like +1, minus 0.1, 0.9, 1.2, something like this. That's what you're going to receive. Let me take it back. I missed one thing here. This noise sample, actually, noise sample actually is a complex value. What I told you here is that noise value is simply just one amplitude value, but noise actually is complex. So for example, it's not like a 0.3. It's like 0.3 plus 0.1 J. It's minus 0.1 plus 0.7 J. Something like this, right? It's complex value. It's like alpha plus beta J. 0.5 J minus 0.3 J. Something like this, right? Noise value actually is complex. This is why the noise will add phase rotation. Each complex value has a phase rotation, right? So even though you, in this case, see that here the phase is 0, but because this noise is complex, noise will add some of the phase. Okay, noise will add some phase. That's why your received symbol will have a random phase. So let's do the same thing. -1 is transmitted. You are adding this noise sample into that. So just add these two. then what you're going to have here is this one. This is what you're going to have. This is the first symbol. Same way, +1 is transmitted, but noise sample is this one, so you're going to add it. This is what you receive as a second sample, something like this. Now let's say we have 1,000 samples like this. What you want to do is you're going to plot. You're going to plot this one in MATLAB. That's what you see here. Again, this is a constellation plot. Let's take a look at the first one. Okay, first sample. Let's plot this first sample. This first sample has a minus 0.7 plus 0.1J. So minus here, let's say this is minus 1. This is plus 1. Then minus 0.7 plus 0.1J, where is it? Minus 0.7 is somewhere here. And 0.1J is going to be somewhere here. 0.7, 0.1J. So that's going to be somewhere here. Now, second point. Second point is 0.9 plus 0.7J. So 0.9 is somewhere here. 0.7 somewhere here. You're going to receive this point. That's the second sample. Something like that, right? So every sample, it's going to be somewhere here, 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 here. Same here, here, here. That's what you're going to have eventually. Okay, when you plot all this is what you're going to see in the constellation plot. So that's what I have done already. So you see the blue dots here. Let me delete this. You see the blue dots? I created like 1,000 samples already and transmit. And based on the noise, I receive that. And this is the constellation plot at the receiver. And what you can see in the receiver here is that the middle point here and here is +1 and -1. So now suppose that if there's no noise, let's say there's no noise, everything is perfect. In that case, what's going to happen? In that case, receiver will have only 1 point here, 1 point here, right? All the symbols, when you plot the received samples, all the received sample will be just 2 points. That's a perfect picture if there's no noise. But because of this noise, right, you are adding some noise. So because of that noise, this sample will be added with noise. Let's say noise is adding only this much of amplitude and this much of phase rotation. When you have that, this point will be moved to here. And that's what you're receiving because of this noise term. So noise will add some of the amplitude. Noise also rotates some of the phase because this is complex value. So that's why instead of this perfect answer, you're going to receive somewhere random points. Here, 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 here. Because of the noise. Then let me ask you a question. This noise sometimes can be very big. Noise can be sometimes very small, right? How do you know? What is the metric that you're going to measure the noise power? SNR, yes, SNR. That's why SNR is important. What is SNR? SNR is the signal power versus noise power. So if your signal power, let's say in this picture, right? What if we have very low SNR? Then what kind of picture do you see? If the low SNR, right? That means noise power is very strong. That's why SNR is low, right? In that case, this, let me call this a cloud, right? This looks like cloud. This cloud is going to be very big, like that. Here, very big. That's what you're going to see when you have low SNR. Okay? If you see high SNR, that means noise power is relatively low. In that case, it's very small like this, very small. If you have a high SNR. So this performance will completely depend on SNR. That's why SNR is important. Okay? Then what's the problem of having this big? Let's say you have low SNR, So your receive symbol is like this way. What's the problem with this? The problem is that if you have very big noise, so that you have very big cloud like this, now then think about how you make a decision. As I said earlier, your decision is very simple. Your decision is going to be like, just put the threshold here, positive or negative. That's your decision. But if you have this kind of high SNR, low SNR, what that basically means is that this is a perfect answer. You transmit +1. But the noise is so big. So because of that, this one is received as here. This is a noise. Noise is so big. So this may go here. And this is what you receive, right? So that's happening when you have low SNR. If you have a high SNR, let's say in case of high SNR, your received sample is somewhere here. It's always somewhere here. So it's very, very unlikely that your sample goes beyond this. Very unlikely. So if you transmit this, but because of that big noise, this sample is received here. That's where you have an error. That's the bit error. So when you have a high SNR, it's very unlikely that you have a bit error. But when you have low SNR, it's very likely you have a lot of errors. Right? So that is how you measure it. So this particular picture is before making a decision. Okay? This is the plot of y. Y looks like this. Y is x plus n, right? So you just directly plot the receive symbol. That's what you're going to have. Now, what you're going to do next thing to do is to make a decision. Then, as I said, how do you make a decision? Cut it into 0, positive or negative. That's your decision. Now you can see here that you see some of the points in between here, right? You see some couple of points here. That is the problem. These things, these samples, no problem, right? Because these things is of course this is a positive, right? You can make a safe decision here. But now the problem is these points. For example, this point. Is it belong to here or belong to here? We don't know. So that's a little bit tricky. And this will always make some bit error. And why does it happen? Because of big noise. This is a random Gaussian noise, right? So sometimes you can have a big noise. In that case, you'll have this error. So that's how to simulate the code. So simply speaking, this transmitter, I think a couple of lines, maybe 2 or 3 lines. Adding noise, just 1 line. You can go just 1 line of MATLAB. Very simple. What about receiver? Receiver also a couple of lines. I'll show you the code in the next slide. Okay? So that's all you need to do. So simulation is pretty easy. And when you make the whole thing in the block diagram, this is a block diagram of a simulator. So we have a binary sequence coming in, like a 0, 1, 0, 1, something like this. And then we create the BPSK symbol. How to do that is, as I said, just do a mapping. Okay? So that's a transmitter. What about the noise simulator? In noise simulator, as I said, we have to use a rand-n function. But this noise is a complex noise. We have to run the 2 rand-n function. 1 rand-n for real, the other rand-n for imaginary. And we are going to add it. That's how you create the complex value. But each one is Gaussian. Okay? So that's how you create the simulation, the noise simulation. But eventually, this is going to be just 1 line in MATLAB. What about the receiver? Receiver is going to be like you receive some signal, and after that, maybe you want to plot it. That's what you have in the plot, constellation plot with the cloud. And you want to do detection. Detection is what's happening inside the detection is plus or minus. That's what you're going to see. Now once you decide plus or minus, eventually you're going to change it back to bits. So eventually output is going to be 1 or 0. Right? So this is the whole simulation. We have a transmitter, very simple, like a bit to symbol mapping, that's it. And noise simulator, just one line of code, like calling random function twice, making real and imaginary and add them together. And then eventually you add that with the transmit symbol. And receiver is this. Once you create this simulation block, now you originally have your own bit sequence. And after all this, you recovered your bit sequence after the whole thing. And what you want to do is that you want to compare. This is my original bit sequence. This is my received bit sequence. So I just compare that. If everything is same, that means perfect. Right? Just compare bit by bit. So that's what you want to do here. Right? Just bit-to-bit comparison. So this whole thing is going to be the simulation structure. Very simple one. One thing that you want to do in addition to that is, depending on the SNR, right? As I said, if the SNR is high, then this cloud is going to be very small. So the error is very unlikely. But when you have a low SNR, this cloud is going to be very big. So you have a lot of error. So now, depending on the SNR, this error is going to be different. So that's why when you do this simulation, initially, you are setting some SNR. Okay, now my SNR is like 0 dB. And then you run it and compare the bit error rate. And then you change the SNR to another one. Okay, now I want to change it to 2 dB. Do it again. And then 4 dB. Do it again. 10 dB. Do it again. So eventually, this whole thing is going to be looping. And every loop, you change the SNR. From 0 to 5 dB, 10 dB, 15 dB, 20 dB. You just keep doing it as a loop. And then for every SNR, you're going to have a bit error rate. So once you do this whole picture, you're going to get this kind of output. This output shows you that the y-axis is a bit error rate. How many errors you have. X-axis is going to be SNR. So when you have a high SNR, that means going right? High SNR, your bit error rate is going to be low because error is unlikely, right? When you have low SNR, you have a lot of errors. So error rate goes up. So it's always, your performance graph, always, in this case, it's like a BR versus SNR. BR versus SNR curve will always like something like this, will always. This is what we call as a waterfall curve. Waterfall curve. It's not important, but it always looks like this. Always. It always goes down. Because SNR goes up, of course the bit error rate goes down. Always. It never happens goes up. Something is wrong. If it goes up, something is completely wrong. Right? So this is the output we want to get from that simulation. So you can do all these simulations. This slide shows you how to do it. Okay? I'll give you some MATLAB code. This is the MATLAB code. Let's take a look at it. First line is just parameter. I just set certain parameter. I want to have 10 million bits. But you can make your own number, right? I just make it as a 10 million bits. The MATLAB run pretty fast. So 10 million, it take only a couple of seconds, maybe 2 seconds, something, very quick. So 10 million is not a problem. Number of bits is 10 million. This is transmitter. Just a couple of lines, right? First line, we have these many bits based on these bits, I call the rand I. Rand I means random integer. Random integer 2. 2 means the upper limit. So when you do rand I 2, that means it will create 1 or 2 in random. It creates 1 or 2 in random, but how many of them? Based on the number of bits. So when you do this, right, this function will run and make a vector, but each value is going to be 1 or 0, 1 or 2, random. Something like this, right? But how many bits? How many samples? These many. Okay? So that is the output from here. But what we want to do is that we want to create a 0, 1, not 1, 2, right? That's the bit sequence we want. So that's why we do subtract minus 1. In that case, this TX bit sequence, eventually, this one will get like 0, 1, 0, 1, 1, 1, 0, 0, something like this. That's the output sequence that I want to have. Right? So this is my bit sequence, just one line. So now my original bit sequence is ready. Next thing to do is we need to do BPSK. And this line, just one line, is BPSK transmitter. So this is BPSK. You can do your own way. It doesn't have to be this way. There are many other ways to do it. So you can make your own way. So I just do it this way. Well, you can take a look at it here, but simply, this is a bit sequence I have. And what I do is that I want to do minus 0.5. So each one, I just subtract it minus 0.5. In that case, this will become like this one minus 0.5, this one positive 0.5, this one minus 0.5, something like this, right? One becomes positive, something like this. When you do this, right? I'm talking about only this part. So when you do this, right, this one will be changed to this way. And why do I want to do it this way? Because I want to do antipodal signaling. Minus plus, like that. And after that, what you want to do is you want to call the sine function. Sine function, this sine, and put this input into the sine function. In sine function in MATLAB, will ignore the amplitude and make it as a +1 or -1. So eventually, when you call the sine with this input, this one will be -1, +1, -1, +1. Because this is positive, it doesn't matter. The value doesn't matter. This function only look at the sign. And all the minus, it becomes -1. Doesn't matter what is the amplitude. Okay? Every negative becomes -1, every positive becomes 1. So eventually, that's going to be output. And I put the minus because I want to reverse the minus sign. But that's based on my mapping. You can do your own mapping. It doesn't matter. And then this is going to be output here. And that is symbol sequence. Okay, I make a symbol sequence. So throughout these two lines, what happened is I just created these many bits. And then based on BPSK mapping, I just create this mapping. So that is a symbol, BPSK symbol. Okay, that's what I have. In here, next thing to do is this one and this one, actually you can bring it up because this one is a parameter. And what I do here is that I want to set my energy, bit energy, to be 5. I want to set it as a bit energy. Because you need to set your bit energy because we want to change the SNR later. And this code does not change SNR right now, but I just make it as a bit energy to be 5. And when you create the TX transmit signal, I just multiply the root square of EB into this symbol. Why do you want to do this? Because this is the signal, this is the symbol you transmit. But before you transmit the symbol, you need to assign some power onto your symbol. And this is how to do it. You make your energy of your each bit to be 5. And I put the root square because this is not the power, this is the actual amplitude. So you want to put the root square. and multiply to that. In that case, you are assigning this much of power into the symbol. Right? So you are changing that. Later, you want to change your SNR. Then what do you need to do? You can simply change this value. Change this value to another one. Then you are changing SNR. So changing SNR, there's a two way. Here's a noise term. Noise power, you make it same. Do not change. Okay? Just make it fixed power for noise and change the signal power. That's one way. Or maybe you can fix the signal power and change the noise power. That's a second way. It's the same thing because that's a ratio, right? Transit power divided by noise power. So change the SNR is there's two way. Fix this one and change this, or fix this one and change that. Doesn't matter. But what I have here in this code is that the noise power, I make it fixed. Only the signal power, I want to change it. So that's why I put it this way. And later, if I want to change my SNR, then I want to change this into something else. I'm not going to change anything in noise. Okay? Change this one. And then run it again and again. By the way, I think this is wrong. This is not SNR 0. This needs to be 1. Then SNR is 0. If you have a 5, then SNR is not 0 dB. Okay? So I think the code is, this one is a mistake. So that's how you create your signal, transmit signal. Now we have a noise. And noise, as you see here, we have a random, which is real component, plus j, another random, this is imaginary. And you had a plus j, right? So that means this is going to be complex value. So this is how you create your noise. Now the question is, what is this one? That's the question. This part is doing normalization. Why do you need a normalization? When you look at this rand_n function, right? Rand_n. When you call this rand_n function, the MATLAB will create these many samples based on standard Gaussian. And standard Gaussian, we know that it's going to be mean 0 and variance 1. Okay? So this rand_n function is using this Gaussian. In that case, what's going to happen is this one, this rand_n has a variance 1. Another rand_n has a variance 1. So when you look at when you do the add these two, the power of this is going to be 2. Because we are adding one Gaussian random variable with power 1, variance 1. Another random variable with the variance 1. So when you add that together, the total becomes the variance 2. So that's why you are doing normalization with this. So you need to do normalization. Once you do this, once you do normalization, now you create the noise signal. This noise signal will be like 0.1 plus 0.7j minus 0.3, something like this, right? Now, when you measure the power, it's going to be 1. I want to make my noise power to be 1. I want to fix it. So that's why you need to have this. You need to have this. You know, if you want to have pi power 1, so you should have normalization. So once you do this, right, now it's time to add them. TX_sig, this is a transmit signal, noise signal. Let's add it here. Transmit signal plus noise signal. Then that's going to be receive signal. Now once you get the receive signal, this is the receiver. Just 4 lines. Receive signal, we put it into here. And what you're doing here is that I just pull out the real component. Right? Just real. Because we have real and imaginary. I need only real component in this case. Because the cosine only matters. Sine doesn't matter in this case. So pull out only real component and put it into the sine because I need only detect the plus or minus. So put it into sine, and then that's how you create. This one is doing -1 and do a sine. That means I'm doing reverse job of doing this. So you can run it. Okay, you can easily find out, what's happening. So that's how you create the receiver. Once you do that, our received bit sequence is ready. Next thing to do is, this is my recovered bit sequence, and this is my original bit sequence. Just compare. Just compare, and count how many bits are different. And if how many bits are different, if you know that, then you can divide by the total number of bits. That's the bit error rate. So this is how to calculate the bit error rate. It's pretty simple. Once you run this, now then you are doing looping. And inside the looping, you change the EB. Okay? And meaning that change the SNR. And do it again. Do it again. Something like this. Once you do that, then you're going to get this kind of picture. We're going to do this simulation as a homework. Maybe you can call that as a homework or simulation project or whatever. But we're going to do this. I didn't put that in the portal yet, but I'm going to put it in the portal. So we're going to have this one as homework. Okay? Just this slide shows you how to do it. And I want you to do that in your MATLAB.